Welcome back. So it's good to be back. I'm really excited about this lecture where we are going to expand the differential equations we've been solving to include forcing terms. So instead of just x dot equals ax, we're going to add the effect of some external forcing or disturbance on the system. And so the forcing could be, it could be a disturbance, it could be a control. So this forcing could be a control input or a disturbance to your system. But we think of it as something that is kind of external to the intrinsic dynamics of the system. And this is going to connect what I've been telling you about differential equations to control theory, which is a huge and important area. So one of the reasons we love dynamical systems and differential equations is because it allows us to model and control the real world. So this is going to be how we transition into that vast literature on control theory. And I have a whole control boot camp. So once you kind of know how this works, you're going to be able to access all of that controls knowledge. Okay, good. And so the kind of differential equation we have been talking about up until now is something like x double dot, I'm going to pick a really easy example, plus 3x dot plus 2x equals 0. And this is known as a homogeneous differential equation because the right-hand side is equal to 0. There's no forcing, there's no disturbance on this system. So we're going to call this homogeneous or homogeneous if you like. And these are the kinds of systems we have been solving up until now, is simple linear differential equations with no forcing. So you could write this as a matrix system and solve that, or you could solve this using the characteristic equation. We know lots and lots of ways of solving this. So I'll put that, there's an asterisk, that's equation 1. And what I'm going to tell you about today is the kind of generalization of this, where we take the same dynamics, x double dot plus 3x dot plus 2x, but now we're going to set this equal to some forcing term, some f of x. And we're going to call this, as you might have guessed, inhomogeneous. Inhomogeneous. Inhomogeneous sounds weird to me, so I'm going to say inhomogeneous. Get those little extra vowels and consonants and syllables in there, inhomogeneous. And so this is what we're going to be talking about. How do we solve the same differential equation, but where we have this inhomogeneous forcing term? And again, that forcing could be something external. Maybe this is a model for how plants grow, and this is the solar cycle, and I know that it's kind of a sinusoidal cycle or something like that, and so I just plug that in. Or maybe it's an external control variable. It's something I actually have control over that I'm going to use to manipulate the behavior of the system. So both of those are valid. Good, and there are going to be two fundamental approaches I'm going to use to show you how to solve this kind of inhomogeneous forced ordinary differential equation. The first method, which I'm going to talk about today, is called the method of undetermined coefficients. So method 1, which is what I'm going to talk about today, is the method of undetermined coefficients. Undetermined coefficients. Basically, it's a fancy way of saying we're going to guess the answer and then figure out a coefficient out front that makes that guess work. And method 2, which is much more powerful but a little bit messier, is called variation of parameters. Variation of parameters. And variation of parameters is going to work for a broader class of functions f of x, and it's also going to be essentially when we solve partial differential equations later using the Laplace transform. We're going to get ODEs whose solutions are those coefficients out front of the solutions, those constant 1 and constant 2. Those are actually going to be transfer functions, and we're going to use the method of variation of parameters potentially to solve for those. But today I'm going to talk about method 1, the undetermined coefficients today, and in the next lecture I'll move on to the variation of parameters. And this is a pretty simple idea. Maybe I'll make this even more concrete. I'll say, an example f of x sorry, this is not f of x, this is f of t. Really, really important for me to be extra clear here. This is a forcing which is a function of time. This is d dt of x, and the forcing is a function of time. Okay, so in that solar example of a plant growing, and this is the solar dynamics, that would be the solar intensity as a function of time that's sinusoidal, not a function of x. And my control variable is something that at each instant in time, I get to decide what that f of t is. Okay, so sorry, I should have made this, that was a typo. So in this example, our f of t, we're just gonna pick something really easy, which is like an exponential function or a sine or a cosine. Here I'm gonna pick e to the minus 3t. And I'm going to give kind of a teaser. We know that if this forcing is something simple like an exponential function or a sine or a cosine, it's probably going to be easier to solve because we know that the generic solution of differential equations is given by exponentials and sines and cosines. So this method here of undetermined coefficients is going to work particularly well, and it's going to be easy when this forcing is one of those simple building blocks of a linear system, an exponential function or a sine or a cosine. And when it's something much more general and nasty, you're probably going to need variation of parameters. Okay, that's just heads up. Okay, so this is the example, and then the last bit of information you're going to need are the initial conditions, which I'm going to say x of 0 equals 2, and x dot of 0 equals minus 4. We may or may not need these depending on how far we get with this derivation. And so this solution to the inhomogeneous ordinary differential equation, it's actually really, really simple. There's kind of 3 simple steps, and they all build on exactly the same kind of thing we've been doing for all of these lectures on how to solve this. So the first step, and this one is completely review, is part 1, we solve the homogeneous equation. So I'll just literally write this in parts. So part 1, or step 1, part 1, is that we solve the homogeneous equation. So solve the homogeneous equation, which is equation asterisk, okay? And so we kind of know what the solution of this is. I can compute the, maybe I'll just write down the characteristic equation. It's lambda squared plus 3 lambda plus 2 equals 0, which implies that lambda plus 2 times lambda plus 1 equals 0. I'm just factoring this out. And so lambda equals minus 1 and lambda equals minus 2 are my eigenvalues. Easy peasy, right? So we solve the homogeneous equation, and we basically have that the solution is x of t equals some constant e to the minus t plus another constant e to the minus 2t. Okay, we know how to do this. And we don't know what these constants are. If there was no forcing, if f of t was 0, we would solve for these coefficients using our initial data, our initial conditions here. But we're not going to do that just yet because we still have to take into account this inhomogeneous forcing term. Okay, so that was step 1. Part 2, step 2, is now we're going to solve for what is called the particular solution, which is a solution, some function that you can plug into here that will equal f of t. Okay, so the homogeneous solution solves this equation equals 0. The particular solution is going to solve this equation equals f of t. So now what we're going to do is find a particular solution, and this is literally called, it's not just a particular solution, it's called the particular solution. That's what it's called in math, a particular solution. And I'm probably going to call this like x subscript p or something like this to asterisk. We're solving the particular solution to the double star equation by assuming that this particular solution xp of t is equal to, what we're going to assume is that it's going to have the form of this forcing term, this e to the minus 3t. And notice that neither of my 2 homogeneous solutions, e to the minus t or e to the minus 2t, neither of those look like an e to the minus 3t. So this is, a different kind of term than either of these. I can't build this as a linear combination of these. So what we're going to do is assume that our particular solution has this form, but it has some constant out front, and I don't know what that constant is. So we're going to assume that this is, some k e to the minus 3t. And then we're going to plug that into this equation and see what that constant is that will make this thing equal 0. Okay, so I literally can just compute the derivative xp dot equals minus 3k e to the minus 3t. Xp double dot is plus 9 k e to the minus 3t. And so if I combine all of those together, all of that information, I have that if I plug in my particular solution here, I get 9k plus 3 times minus 3k is minus 9k, plus 2xp is plus 2k, all of that times e to the minus 3t. That's everything on the left-hand side. That has to equal my forcing term, f of t, which was e to the minus 3t. And now I hope you're kind of seeing why we guessed that the particular solution had this form, because we know that if our particular solution has this form, if I take its first derivative and its second derivative, it will still be of the form e to the minus 3t. And so by choosing this constant k carefully, I'll be able to find this particular solution that if I plug it in, all of these terms will add up exactly to equal e to the minus 3t. Good. And so I think that means this out here is just something like 2k e to the minus 3t equals e to the minus 3t, which implies that 2 times k equals 1, so k equals 1/2. So my particular solution is literally 1/2 e to the minus 3t. That's my particular solution for this problem. Okay, so that was part 1, solve the homogeneous equation. Part 2, find the particular solution. Part 3 is kind of neat. Part 3, what you do is you combine these two solutions because these are both, this is a solution of my differential equation that satisfies this equals 0. This is a solution of my differential equation that satisfies this equals 0. And this is a solution of my differential equation that satisfies this equals f of t. And so those are all solutions of my differential equation, and I can take a linear combination of those, and those are still a solution of my differential equation. This is the fundamental property of linearity. These are linear differential equations, and so superposition holds. If I have two solutions, then I can add those up, and those are still a solution. And so this is really important, is essentially if I take my homogeneous solutions and I add those to my inhomogeneous solution, they still satisfy this blue equation here. So I can add this constant here to this term, and when I take the derivatives of this pink term, they add up to 0, so they don't mess up this blue term also being a solution. So this blue term plus this pink term are also solutions, because if I take the derivative of the sum of all three of these terms, these add up to 0, and this still adds up to f of t. So that whole solution adds up to f of t. Okay? And so that's really important, is that the full solution, so I'll write this down, part 3 is to add up all three terms. And so that gives me something like, maybe I'll just write this in blue, x of t equals c1 e to the minus t plus c2 e to the minus 2t plus this 1/2 e to the minus 3t. And notice that this doesn't have just an arbitrary constant out in front of it. We determined this k constant has to be 1/2 to satisfy this exact forcing term e to the minus 3t, this inhomogeneous forcing term. So every solution has to have this term in it to add up to equal f. And then that solution can have any constant e to the minus t plus any other constant e to the minus 2t, and this is definitely a solution. So you could, right now, if you wanted to, you could pause the video and you could take this expression here and you could compute its first derivative and its second derivative, and you could plug it into this equation and convince yourself that these two terms here from the homogeneous solution, they add up and they don't change this f of t. They don't mess up this equaling f of t. And because we have this term here, the solution definitely adds up to equal f of t. So any x of t of this form will solve this equation. And part of this last step now is you can determine these coefficients uniquely using your initial conditions, just like we would before. But when we do that, we have to solve for these in this equation that has all three terms, not in this equation up here that only has two terms. Because our solution has this extra inhomogeneous term here, this extra term, it's going to kind of change these coefficients needed to satisfy these initial data. So let's just confirm. OK, so x of 0, if I plug in 0 to this solution, now I have that equals c1 plus c2 plus 1/2. And that equals 2. And x dot evaluated at 0, I'm just going to read it off because x dot is minus c1 da 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 plus minus 2 c2 da 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 plus minus 3/2 e to the minus this. So I can just read this x dot off. That's minus c1 minus 2 c2 minus 3/2 equals minus 4. And again, I chose these initial conditions to be easy to kind of evaluate this. So if constant 1 is 1/2 and constant 2 is 1, then both of these are satisfied. So c1 equals 1/2 and c2 equals 1. But notice that I had to use this expression that had all three terms. After I found my particular solution, I had to have my particular solution to evaluate x of 0 and x dot of 0, because that term is going to add this 1/2 or this minus 3/2 to those. So I need to have this particular solution in my expression before solving for these coefficients using my initial conditions. I can't solve for my constants using my homogeneous solution. I need to have that particular solution in there too, because that affects my x naught and my x dot naught. OK, that's it. That's the method of undetermined coefficients. It's super easy. You write down, you solve the homogeneous part of the equation. Then you guess that there will be an extra term that looks like you're forcing, but it has an undetermined coefficient. So you plug that into the equation. You solve for that constant k. Then you add up all of those terms, and you use those to find your coefficients with your initial conditions. A good example for you to do would be, so if these are simple exponentials, it's pretty easy. You just guess that exponential. Another good example would be to try, what if this equals something like, cosine of omega t. So I have some forcing at some frequency, cos omega t. Now, when I try to solve for my particular solution, your xp of t, we know that the things that are going to, the functions x of t, where that function and its derivatives look like cos omega t, are going to be things like cosines and sines, right? Because the first derivative of cosine is going to be a sine. The second derivative is going to be cosines again. So in my method of undetermined coefficients, if my forcing is a cosine, I'm going to need to actually have some constant a cosine omega t plus some constant b sine omega t. Okay, and you're going to essentially plug this whole thing into your expression here, and then you're going to solve for a and b so that all adds up to equal cos omega t. So that's actually a really good exercise for you, is do this exact same procedure, but assuming that f of t equals cos omega t. And in this step here, where we assume the particular solution has this form, try it out. First off, try it out with just a cosine omega t. You'll realize that something goes wrong. And then try it with a cos omega t plus b sine omega t. And then you'll be able to determine that set of particular solutions. You'll add them up. Now you'll have 4 terms because you'll have a plus a cos omega t plus b sine omega t. And you'll use that to find your constants with your initial data. So that's a really good exercise to make sure you understood how this all worked, is to try it with f of t equals cos omega t with this particular solution. Okay, in the next lecture, I'll show you how to do variation of parameters. So that's coming up next. Thank you.